Okay, we're on. Welcome everybody for the next in the CREDC seminar series. Happy today to introduce Tim Yardley. And my standard joke when I have somebody like this is, the man who needs no introduction, and so we won't get one. But there are people that maybe don't know him, and so give him somewhat of an introduction. So Tim has been with ITI for a long time. Actually, as far as his degrees, if memory serves, he was here as an undergraduate, got a degree in computer science, if I remember right, and did a master's degree from someplace else while he was here working. So managing degree work and family all at the same time, that takes quite a skill set. In any case, Tim is the Associate Director of Technology here at Information Trust Institute. CREDC is the third in a series of centers focused on cyber security, cyber resiliency, and energy delivery systems. And Tim got involved with the first one, TSIP, and started to build up the test bed that we had, equipment and software to help the researchers evaluate and develop their stuff. Got into TSIP-G, and that effort grew remarkably under Tim's direction, and he could probably tell, I'm certain he could tell you the number, but millions of dollars of donations in equipment and software to give us a test bed that is the envy of all academics. And indeed, it was the work that he did develop in that test bed and encouraging people to use it that brought us to the attention of DARPA. So when they had a program, RADICS, that called for a test bed on which to have developers, have other performers have their work evaluated. They came to us to talk to us what the needs were, and naturally then we had a very competitive proposal to them for that piece of work, and that's what we have. And so Tim is leading that effort, and it is something like 18 million, 19 million, somewhere in that range. Maybe there's a larger number, but it's a big effort, and it's a very large responsibility. So we're glad to have him here. We're glad to have him here doing the things that he's been doing, and he's here today to talk to us about his ideas and visions in that space. So with no further ado, Tim Yardley.
Thank you, David. So as David mentioned, we're here to talk about cyber-physical experimentation. In this particular case, I'm talking about innovation that's been enabled by the DARPA RADICS program. But really, this is a glimpse into the future of cyber experimentation and what the evolution is from past state of art to where we are today and where we're going in the future. So first off, what we're trying to do is really to advance the state of art. So CEER, the name of this particular project, is trying to change the game. So instead of being a system that is represented based off of fictitious scenarios and reference implementations, creating tools, techniques, and methodologies that allow us to let's say, extract reality from the real systems and then manifest that in these environments and recreate those at a new level of fidelity and a new level of rigor that wasn't capable before. So really focusing on that generational leap forward, not just an evolution. So what are the three areas that we're focusing on? Well, the three areas are primarily usability, capability, and rigor. So usability, the key there is trying to make testbed facilities that can be used by any researcher, not somebody who is an expert in setting up testbeds or testbed environments. To really change that point of view where you can create an experiment, drag and drop in essence, and click go and start your research and focus just on your research, not have to worry about all of the mechanics that have to get you to the point to set up the environment that you can use for your research. On the capability side, there's all sorts of capabilities that we had before this initiative and that we were developing over the past decade, but they were focused in particular ways and limited in other ways to allow us to sort of accomplish certain missions. In other words, there was research that we wanted to do that we couldn't quite do or couldn't quite prove out in the way that we wanted to prove it out with the capabilities that we had. So expanding those capabilities is paramount in terms of moving forward. The other is rigor. So it's one thing to prove out particular research that you're doing on a particular environment or a particular setup, but imagine the power of, all right, I ran my research against this topology. Now and it came back with a positive result. Now I want to take and run that exact same experiment against 1,000 or 10,000 or 1,000,000 different topologies that all represent real-world configurations and different nuances of real-world configurations. And they're all semantically valid for the real world. And I want to see if my work works in all of those edge cases, all of those different environments. And be able to press a button and it just goes and does it. You don't have to redo this 10,000 times or 1,000,000 times manually yourself. And to be able to prove out that this work not only works in those environments, but that you capture the results as well, so that other people can build upon your work, other people can validate your results, or look at the data associated with your results and see if their work can improve on that. So where is the state of testbeds today, or where are we today in relation to solutions? And why did we have to evolve? Why did we have to do this generational leap forward? So why testbeds of current time generally don't work for this type of problem is they're not true to reality. They're using reference cases or static models. So they also can't scale. They're built with a particular topology, and it's difficult to uplift or re-architect the system in terms of a different topology. They also require you to be somewhat of an expert to even begin to use the environments. They're not designed to be user-friendly inherently, or if they're set up in a particular configuration, you're constrained in what you can do, rather than you being able to do what you need to do in the particular environment. Another aspect is that they're generally not accessible, and by that I mean you have to be physically at the testbed in a lot of cases, and you probably won't even be able to physically be at the testbed unless you're paying for that access or you're directly doing research with the people that have that testbed environment. In some cases, you also can't go to some of these testbed facilities unless you're a US citizen or other constraints similar to that. The last part is a little bit in the weeds of technical detail, but there are a lot of really good power testbeds out there. And there are a lot of good cybersecurity testbeds out there, or tools in either of those domains. But these testbeds are good in that single axis. It's hard, or there exist very few that are good in both the cyber and physical axes, and that treat them equally and operate them cohesively together. So our solution to the problem is looking at testbeds holistically. So a lot of people also have the misnomer that testbeds are equipment in a room configured in a particular way. And yes, that is true. That's part of what a testbed is. But a testbed is also the data that drives it, the data that helps you create these models, the data that helps you prove out these systems, the assets, that those physical hardware, software, et cetera, that's there, the people that understand how to configure this and the knowledge that they bring to bear, not just in terms of the technical resources of the testbed itself, but also of industry and the people that are the practitioners in the field that set up and configure these systems. And there's another core aspect, which is the science problems that have to be solved. So federation, cosimulation, data coherency, data expansion per se, or contraction of data sets into manageable pieces, extracting metadata from information and real systems, and using that to create profiles. All of these are things that have to be solved or have to be pulled together in terms of a coherent solution to realize these environments. So all of this holistically is the testbed itself, but the testbed's nothing unless you have the ability to serve the customers and the ability to manifest those resources in the ways that the customers need. So customers drive the needs, and those customers are the researchers or the technology that needs to get proven out. And science, data, assets, and people help solve those particular problems by creating the systems that enable that. And then the testbed produces or outputs that solution, that environment that's configured to support the research. And it can do that either by provisioning resources in the cloud. Typically, that's more on the testbed operations support stuff. It's not the actual experiment, but we can do the experiments in the cloud to a certain degree as well. And then provisioning local resources as well. And those local resources may be IT resources or OT resources in terms of PLCs, IEDs of various different types, et cetera, or computers, virtual infrastructure, et cetera. So I mentioned people as being an important role. So these are people that are part of our team. And I want to key in on the fact that this is a multidisciplinary team. There's computer scientists, there's power engineers, and there's system administrators, operators per se, that are enabling us at Illinois to accomplish what we're doing. But the people just at Illinois are only part of the picture. It's really all of the world that is helping us in some way, shape, or form. And why do I say the world? Well, we're using tools that other people have developed. We're extending those tools in various different ways. We're using technology that other people have developed, problems that other people have solved, resources that other people provide that help us bring this together. And we're taking knowledge from the practitioners, the utilities, the asset owners, et cetera, and encoding that in ways that we can then programmatically build and respond to needs of researchers by leveraging that knowledge to create the new topologies and systems. So David started out by mentioning that this is long in the works. So we started in 2005, roughly, with the building the testbed. And it started out as a couple pieces of equipment that really came, I think, somewhere in the 2006 sort of time frame. And so there were a couple relays. There was a computer that was running an EMS, and they were configured in this static environment, sort of substation A and substation B. And so I joined the team in roughly 2008 and started to grow the testbed, evolve the capabilities, and turn it into a tool that was supporting our research, but also pushing our research in some ways. And that sort of ebbed and flowed. In 2010, we started to open the testbed to other people. So entities that were not directly doing research with us would come in and prove out their work. Sometimes those were national labs, sometimes those were other academics. In 2016, there were multiple awards that came that sort of looked at refining and expanding our capabilities. So the DARPA program being one of those in late 2016, and full award at that point, and also CREDC, what we're here on the seminar-wise, moving from just the electric power grid, which was the initial focus with TSIP and TSIP-G, to broader energy delivery, so looking at oil and gas. Now, our testbed actually was broader than electric power grid for quite some time. We've had nuclear controllers, the Invensys Triconics platform. We've had systems of other types that have come and gone through the facility. We've brought in quantum cryptography gear and looked at that in relation to grid operation and application with the National Lab, and lots of other things. And one of the keys is that a lot of the resources that are in the lab aren't necessarily grid specific either. So PLCs are used broadly in industrial control systems, and the same PLC is used in the electric power grid as what is used in manufacturing and used in other segments as well. So our future is really to expand these capabilities beyond what we're working on just in the electric power grid and oil and gas delivery, but to look at other critical infrastructure domains and how the techniques that we're using can be further generalized to be able to support and provision those types of profiles as well. So what's the real reason behind why we're building or evolving this? And the reality is that we're dealing with protecting critical infrastructure. Critical infrastructure is, by its pure definition, critical. And to the tune that it is mission critical that the technology that we're using to protect that critical infrastructure works, right? And why I say it's mission critical is people can die if this type of technology fails. And if we look at technology under the RADICS program, so RADICS, just very briefly, is looking at post-event technology. So the grid has been attacked. How do you determine that attack is happening? How do you determine what the attack was, what it caused, what it affected, what the systems are that are tainted or not tainted, what the intruder is doing at that moment, and how to restore and remediate those actions globally? So in other words, on Prevention, you can sort of be on the edge, and you know exactly what the attack vector is. But if you're dealing with an attack that already happened, you didn't know what that attack vector was, you didn't know what they were exploiting, you have to root it out and figure it out, which means your systems need to be even more real. But these tools that are being proven out on the response side, these things that need that additional level of detail, when we call upon those to use those in the field, that's because the grid has been attacked. And that may mean our lights are out, that may mean that parts of the US are blacked out, it may mean a lot of different things. But how much do you want those tools to work at that point? Or how much do you want to spend time with developers going back and forth and saying, well, you know, I think there's a bug here. Let's see if we can figure that out and see if we can get this tool working in the next month. No, right? You want these to work from moment one. So they have to be proven out before we need them, before we have to bring them to bear to help us. And so the other reason why we have to do this is that the technology, the capabilities in testbeds just doesn't exist today. It's not fully available to prove out the tools at that level of rigor. And the reality is that we can't do this on the real grid. It's too hard, it's too expensive to do it on the actual grid. So we have to have something like a testbed that enables these types of environments and to be able to rapidly re-architect them based on different architectures, different utilities, different areas of the country, different problems, different scenarios. And we can't go through months of engineering time to rewire and re-architect these systems. They need to be able to be re-architected on the fly, on demand as needed. So a testbed is essential to that. So what is our approach? Well, our approach is one that's hinged on flexibility. So we have models. The models drive the experiments. And a model is the actual real system configuration in some cases, the real one-line diagrams, all abstracted so that you're removing the critical information from them, but still statistically equivalent to them. In other words, the topologies and relationships are maintained, but the geographic location is stripped away because it doesn't really matter for the sake of an experiment as to where it's geographically located. The other aspect is modularity. So modularity is key in that if we want something that's recomposable, something that's flexible, something that can be varied based on the needs of an experiment, then you need to break it into pieces that they can piece together to form different puzzles or different pictures, right? And that needs to be ideally done in a self sort of described way so that the researchers don't need to understand how to put these pieces together. Puzzle pieces, as you likely know, you can't just take puzzle piece A and puzzle piece B and put them together unless they were cut to be together. So how do you either make it so that these things that weren't designed to put together have glue that can glue them together and hold them together, or make it so that they're universal so that anything can plug in with anything else? Another key aspect of this is instrumentation. So you have to collect data on what's going on in order to prove that it worked, right? Inherently, these industrial control systems are opaque in many ways. You don't know what's actually going on in different aspects of the system without poking into those areas of the system. And if you look at real world, some of the experiments that we need to prove out and validate, in the real world, they don't collect the type of data we need to prove that the system works. And so even if you were to deploy this in the real world on the real systems, you wouldn't be able to prove out that your stuff works, because it either wouldn't see the case of what you need it to do to prove out that it works, like an actual cyber attack, for instance, or you wouldn't be able to collect the data to do the analysis because they don't have the instrumentation to be able to do it. And so the last part is knowledge. I mentioned that knowledge is key. And so we have a blend of academic, enterprise, manufacturing, and asset owner knowledge that comes together to give us the best of each of the worlds. So instead of us trying to ascertain what a particular product is doing or how it works internally, we ask the creators of the product to tell us that information, and then we can incorporate emulation of that, virtualization of that, or just a deeper understanding of the behavior of the system or nuances of that system so that we can create more realistic, more represented, and better instrumented experiments. And it's key to have that multidimensional approach. So I mentioned that usability is important and capabilities are important, so I want to give you a bit of a landscape. The gray dots are charting of some of the other testbed facilities, major testbed facilities in this area. In 2016, we were that orange dot in the middle there, pretty much the farthest on capability and almost the highest on usability. So these aren't arbitrarily placed. There's quantification to these numbers. And so I went through and sort of assessed where we are today with our 2017 facilities. And now we're at roughly that purple dot. We've enhanced a lot of capabilities, and I'll talk a bit about those in a moment. And we've enhanced a bit of usability, but we're not quite as far in the usability side as we have been in the capability side. Our target is that far upper corner, the green dot. We have roughly 3 more years to work on that green dot. And so we're well on our way, but we still have a long way to go. And oh, by the way, this isn't a linear progression either. It gets harder and harder as you're going further and further down the capabilities and further up on the usability. So what's available today in the testbed? What do we have? So a quick 10,000-mile view is there's a room with equipment and a room with desks and chairs and a room with TVs and monitors of various different types that allow you to visualize and demonstrate and do things. There's VPN access, remote accessibility to the testbed. There's storage, there's computation, and there's ICS-specific gear, right? We also have the ability to bring in other people's stuff and plug it in and use it in an experiment and realize that. And there's dedicated office space as well for researchers that are working with us on particular things. From a network perspective, we have very fast uplinks, 10 gig E uplinks, and 10 gig E fabric amongst the core switches in the system. Everything is SDN enabled, software-defined networking. So we have sort of next generation architectures for looking at networks from that perspective, but we also have the legacy capabilities of standard isolation and segregation and VLANing. Dedicated VPN access that I mentioned before. All sorts of broad capabilities. So I like to say that we have full end-to-end smart grid capabilities. In other words, we can look at generation, we can look at distribution, we can look at transmission, we can look at consumption in varying degrees. And we can look at those combined to certain levels of combinations. We have advanced metering infrastructure, we have solar research platforms, we have the ability to have real gear, emulated gear, et cetera. We have modeling software of various different types. We have fuzz testing tools, communication technologies. And then we also have a fiber optic link to a real testbed. By real testbed, I mean an on-grid substation, 12 kV substation at the Ameren Technology Application Center, and we have some equipment over there as well. And so we have a fiber optic link to that facility. So if you look at hardware and software, and I'm not going to go through and read all of these, but basically everything that's out there that's used commonly in research or that's used commonly in the actual asset owners or utilities, we have in some way, shape, or form or can acquire in fairly easy manner for the most part. So that includes high fidelity power simulators, it includes network simulation tools, it includes EMSs and DMSs, it includes data historians, it includes AMIs, MDMSs, security testing fabrics, federation tools, PLCs, security gateways, firewalls, blah, 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 blah. So if we break that down a little bit in silos, control center-wise, we have OSI Monarch EMS, Pi Data Historian, we have visualization softwares of various different types, and data management or data aggregation systems in various different ways, Cygate, OpenPG, OpenPDC, OpenHistorian, et cetera, as some of those examples. On the generation side, we have an isolated solar test lab that allows us to look at microinversion strategies and inversion strategies. We have an external solar array, which is a 20 kilowatt solar array broken into 5 separate strands, allowing us to look at real-world inversion rather than just a single panel. And that also feeds an operational building, so we can do some demand response related stuff there, or look at load demands on distributed generation. We have transmission and distribution gear. This is slide 1 of that. There are 18 ABB Ref 615 relays as an example, COM 600s, which are substation gateways, Arbiter PMUs, GE relays, D60s and F60s. One D60 is actually an N60. We have Novatec Orion LXs, which are sort of a substation gateway, sort of a PLC on steroids. Similar to the SEL-R TAC, which I'll talk about in a moment, or similar to the Eaton Cooper SG4250 substation gateway, or the ABB COM 600 that I already mentioned. Schweitzer Engineering gets their own slide just because of the amount of Schweitzer Engineering gear we have. So we have all sorts of GPS clocks, substation computers, relays, adaptive multi-channel sources, automation controllers, encrypting devices, network switches, et cetera. And the list of equipment is constantly growing. This isn't even quite fully current. Advanced metering, we have Itron's OpenWay architecture, which is the prior generation architecture. So that's prior to the Cisco re-implementation. We have 4-cell relays in the MDMS from Itron Enterprise. We have Trilliant Test Bench, which is an AMI harness. We have our own smart meter research platform, and we have protocol stacks in other realms too, C1222, DLMS, COSEM, protocol stacks broadly. So let's speak about protocols for a bit. There's a lot of industrial control system protocols that are out there. We have binary or source test harnesses or protocol implementations for all of these mentioned here, and some proprietary ones that just get lumped under the proprietary sort of category. All sorts of modeling. We have an Opal RT 5700 that's fully loaded. We have 2 RTDS chassis, which are well optioned. We have 4 Doble F6350Es now. We have 2 F2100s as well that are on loan to us. We have a Pacific Power 4 quadrant amplifier for source and sync. Lots of modeling software, and then we have cyber-related stuff too. Some homegrown, some standard stuff like NS2, NS3, GNS3, Emulab, Deter, Core, et cetera. So not all fully listed here. Security specific, we have all sorts of security tools and ICS specific products that are available out in the market that we bring to bear to accomplish different things. And then we have, I list OpenFlow as a security specific tool for a couple different reasons, and I won't go exactly into why, but OpenFlow can be used as both a security monitoring fabric as well as a segregation fabric. We have all sorts of computation capabilities. We have over 60 high-end servers, and by high-end servers, I typically refer to them as dual processor, 10 to 12 core machines per processor, 128 to 256 gigs of RAM per machine, centralized storage, 10 gig interfaces, et cetera. So that's sort of our high-end server notion. Some have more RAM than that, some have more processing power than that, some have faster drives or more storage than that, but that's sort of the baseline for it. And then we have federation of assets, and we use an enterprise grade system for federating, or for provisioning, I should say, assets. And then we have federation technology that we're working on in the research side to link together different facilities and different pieces of research, either in a cosimulation perspective or site-to-site sort of federation of resources. All sorts of miscellaneous gear as well that enables us to do various different things. I won't spend any time on this. And then we have unique integration, special builds of tools, special builds of firmware, et cetera, that allow us to accomplish or poke deeper inside some of these devices or capabilities. We have full lab packet capture capabilities, which allows us to do intrinsic data capture across the facility, and we have software-defined radio capabilities as well that we've brought to bear in AMI research and other things to do white space radio related stuff and others. So to talk a little bit about usability, one of the things that we've done is created an onboarding process by creating a testbed portal that allows people to request accounts and gain access to the knowledge base and get help from us as a team that's responded to in somewhat real time via Slack system. And have ticket reporting and other aspects. So that's been a great onboarding process that's helped save time of our researchers and save time of our operations staff to be able to deal with that. So let's talk a little bit about power system modeling for a bit. So really what we're doing with power system modeling is we're trying to support that advancement mission that I talked about before of advancing research, advancing verification and validation with deeper rigor, and doing this specifically with a cybersecurity focus. So with these models, we really are trying to generate realistic scenarios. So not just using an IEEE reference bus as an example, but building real topologies modeled after real systems and looking at the nuances of how the real world is configured and how that differs from what reference models provide for us. And doing so in a way that still allows us to share the models and share the data and the output from these results. We have to have the ability to support communications traffic, so those protocols I mentioned before. It's not that, oh, I just care about the power data. Remember, we're looking at things from a cybersecurity perspective, so I care about the data flows and how the systems are communicating at the cyber level, not just what the power telemetry is. And then we also need the ability to drive real hardware as part of what we're doing. So we have the interfaces and the ability to drive that hardware as hardware in the loop simulations to support that effort. So there's all sorts of tools that come to bear for that. Most of these I've mentioned already, so I'll just stay on this slide for a moment. They really break these tools down into two sort of domains. One is what we would refer to as sort of the slow simulation tools. So where you're getting data not necessarily in real time, and you're not necessarily stepping at the lowest level of fidelity to catch nuances and dynamics or whatever it may be. And then we have the fast simulation tools. And the fast simulation tools are the things that can drive hardware in the loop, as an example, or to get into the dynamics or the transients of the system and allow us to look at those nuanced behaviors that happen. And we bring both of those to bear in different ways. And we're exploring techniques to be able to link those two different fidelities together and run coherently together. So communication, the simulators have different abilities to communicate, some of which are proprietary, some of which are via common protocols, and each of those has benefits and drawbacks. So if you want telemetry, there's ways to get telemetry, say, as a CSV output, or there's ways to pull telemetry from the internals of the system and extract those directly, or there's the ability to query it via standard protocols and get telemetry via, say, standard mechanisms, but not at the type of granularity that you would be able to get via the other ways. So we have to have the ability to do that in multiple different ways and interface them with multiple different systems. So there are modeling cases that we've released under past efforts that we're expanding. And so these used to be homed on a center page called the Illinois Center for the Smarter Electric Grid, ISEG. I've now pushed those to a GitHub location to ease the ability of reuse of them and forking of those. So we now have a GitHub page, github.com/iti/models, that serves as a home for this. Now you might ask, why is it called models rather than, say, power system models? That's what we're talking about here. Well, the intent is that this will be the home of those cyber models that we release, the overlay infrastructure, and not just the physical models. So what's up there right now are power system models from that prior work, and we'll be putting up more power system models in the near future. A lot of the models that are there are reference models and synthetic models that have been created, and they're created in those small, in the, let's say, slow modeling tool formats. We'll be releasing RTDS cases and OpenRT cases in the future as well to enter that second domain, and then combining those with cyber tools that are setting up overlay networks and infrastructure that models that as well. And I'll talk a bit about those cyber tools now. So from a cyber perspective, data generation is one of the key things that we need to do. So I can't run a hardware in the loop simulation all the time. One, they're not stable enough to run 24/7, 365. And two, they're expensive. So an RTDS rack that we have runs us about $250,000. The OpenRT unit that we have is in the millions on how it is optioned. And RTDS units easily go into the tens of millions as you scale in terms of capacity. And they inherently can be used by one project at a time concurrently, right? So you get one person that can benefit from that resource while it's being used. So it's hard to scale that. And I can't run a project 24/7, 365 that's using that resource, because then it's not available to anyone else. So how do we take the stuff from those resources and turn it into something that enables everyone? And so the answer to that is telemetry extraction and modular sort of creation of events and scenarios and libraries of things that we want to do. Those models are a start for that, and the things that we'll be releasing in the future are effects on those models that allow you to look at different things, like different trip scenarios and other potential disturbances on the grid that allow you to evaluate your tools against that. We also hope in the future to be releasing large data sets that'll be linked in each of those models, which are telemetry captured from running those models in case you don't have the software to run those models, and allow you to reuse those with the tools that we have that are generating traffic. So what are those tools? Right now we have a DNP3 and a Modbus protocol generator that can replay these telemetry, and we're going to be open sourcing those soon. And then we have a commercial product that we use as well called DTM from Triangle Microworks that's really a great useful product from the perspective of ease of use. It's a GUI, it's point and click, and you get real simple setup. It's not quite as flexible or as powerful as the type of things that we're developing, but it's a wonderful platform and it's using commercial grade stacks. And so we have a number of licenses to that we bring to bear. And then our tools will be open sourced here in the near future, and they're based on other open source tools. So this is just a further extension of other people's work built in the way that we need to do. Now, one of the interesting things with this is we have flexible data generation rules, and we embedded Lua internal to the data generator, so you can programmatically change the behavior of the generator, manipulate values, manipulate how the system is working, modify data, do intrusion attacks or injection attacks or other things that may happen. And then we also have the ability to replay telemetry on the DNP3 side, and soon to have that ability to replay telemetry on the Modbus side as well. So this is a little mock-up that we did using DTM. We created a power station in essence. And so this is a central control center, in essence, of 4 substations that are providing information. And this is set up all in the DTM environment. So this is an HMI in DTM, and it's querying out to different aspects that are all modeled in DTM. And also we have the ability to hook this up to the RTDS or the Opal RT and query those systems in that same way. So we can build these HMIs or these control operation sort of perspectives and control logic on what we're doing simply with a tool like this rather than going through heavy lifts. And so that's really useful. But what's coming in the near future? Where are we going with this stuff? So I mentioned that we have a professional platform that we're using for provisioning. So we do have that. It's not yet provisioning the physical stuff. It's only provisioning the IT. So I'll talk a bit about that in a moment here as soon as I finish taking that drink. So that platform is in essence a spin out of MIT Lincoln Labs that was funded. The original sort of design of this type of thing was funded under the National Cyber Range, which was a $130 million program focused on trying to solve these types of problems. And so MIT Lincoln Labs spun out some people that created a new implementation of this that was designed to be more flexible and more usable overall. And that company is called SimSpace. So we've partnered with them on the DARPA RADICS program to build out environment capabilities to provision OT systems, not just IT systems. So what they had the ability to provision when we started with them was basically just VM infrastructure in the cloud. And so we now have an on-premise install of their stuff, and we have the ability to bring in physical assets, and we are working on the ability to provision, let's say, the industrial control system side or the OT side of those assets and bring those seamlessly into experiments in different ways. We also have brought a new level of rigor to their platform by specifying needs that we have for reproducibility and other things that support scientific work rather than just, say, one-off ranges that are spun up. So being able to recreate the same environment every single time if you want it to be that way, or the ability to vary that environment if that's what you want to do in relation to how that experiment is provisioned. So they've been a great partner, and we're looking forward to incorporating that with the physical provisioning stuff that we're working on, but it's not quite there yet, so we're still working on that. And so we're also building these deployment profiles, these different layouts and topologies that you'll be able to mutate, taking sort of an ontological view to representing these and reasoning about them at a metadata sort of way to maintain relationships that happen, but to be able to perturb and say reconfigure those topologies in various different ways. And then in theory, dynamically and automatically map configuration changes to those as well. So as you change topologies, the config variables and config values can get changed, a la set points and other things. So being able to automatically recompute what those new set points would be based on how an engineer in the field would actually do it is important. And in theory, if we do this in a flexible enough way, you should be able to take configuration from application number 1 and say, I want to use application number 2, vendor number 2, to replace that one, translate the config from vendor number 1 to vendor number 2, and maintain the properties that I need to have maintained. Will that work seamlessly? Maybe not, but it hopefully will give us a good starting point that gets us to a configuration. And then assets. Assets are obviously key. We're getting more assets than what we have, and assets are both a hindrance and an enabler in various different ways. So assets are an important role in there. So let's talk for a second about vision. So that's where we're going in terms of what we have immediately on the horizon. But let's talk about where we want to go in the end. So really, to recap on what I started with, is we're seeking to advance the state of art. We're not just looking to evolve, we're looking to take a generational leap forward. We want to increase the usability through these tailored tools that we're creating and seamless integration of systems that weren't designed to link together. We want to focus on the development and integration of modular pieces so that you don't have to take the entire experiment and use the entire experiment if you only care about a piece of it. Or if you only want a piece of it to plug into your environment, you can do that and use it in that way. We have to drive these models and their conditions from real telemetry. And what I mean by real telemetry is actual data from real utilities that give us how the real systems are operating and then mimic that exact same operation down to the nuanced detail. Pole intervals, buffer queues, deadbands, et cetera, all of that come into play. Nuances of the system, squirrels that get fried, devices that are in maintenance failure, et cetera. All of that we want to be able to recreate faithfully because those are real world scenarios that you may need to deal with. We want to incorporate and extend work done by other researchers. So what I mean by that is that it's not just that we want to build the field of dreams and everything that we do is what you have to use, right? We're happily reusing stuff that other people have open sourced or made available to us in some way to reuse, importing that to our environment and making that better than what it was when they had it or more tailored to the type of work we're doing. And we want to then contribute that back to them as well and back to society as a whole so that we're not just taking things, but we're making things better and giving it back to the world to save them time as well. We tackle all sorts of difficult problems as researchers, proving out our work. And I know all of us have struggled to adapt something to meet our needs. And then when we finally got it to meet our needs, we proved out our work and then we moved on. But what I want to do is capture that so that the next person who wants to do something like what you're working on doesn't have to repeat all that effort that you struggled with to get working. We can reuse that and move that forward. And so that's part of the documenting and packaging experiments, right? We need to drive research with reproducible, releasable, and recreatable experiments. So it's not just that you can prove out your work, but we want to be able to have people cross-check your work and expand on your work and evolve your work as well. And we have to develop environments also that aid learning and research understanding and translate further to operational advancement. In other words, we don't want people to think that they have to be experts when they start. We want to be able to create environments that let them learn about these and evolve and move forward. And I think all of those are key to really creating environments that persist well beyond the research that they were used for. So in terms of future capabilities, multi-access converged modeling is one key aspect that we're trying to solve. We want to be able to take data and extrapolate it. So in other words, take 10 minutes of data and turn it into an hour of data, or 24 hours of data, or 10 days of data, or 10 years of data, and be able to do that by bringing in externalities and varying based on seasonal basis, weather patterns, et cetera, that could influence the operation of the grid in various different ways, including software patches and changes to telemetry, monitoring, and other aspects that could come into play. We want to have seamless coherency between the cyber and physical. So those are things that we're still working on right now. They operate together, but they're not seamlessly together. They're still sort of self-contained, but linked. We are working on some detailed sandbox environment stuff, and I'll talk very briefly about that here in a moment. We want to use more or get more true to reality utility architecture. So we've reached out to a large number of utility contacts and friends who are sharing data with us, sharing topologies with us, et cetera, to really take that next step in looking at not just what one area of the country looks like or what a handful of areas of the country look like, but what does a generic utility look like in different ways, and what can we capture from each of those? Or if your research is looking at solving a particular problem that's only evident in one area of the country, that you can run it on a model that has those particular nuances or those particular behaviors. We want to enhance the data generation, injection, and correlation tool capabilities that we've been building. And we also need to build or want to build experiment data analysis, collection, and processing tools so that instead of you having to understand how to extract the data from the system in all these different ways, it will extract it for you, package it up, and even do some initial analysis for you, showing some trending information or whatever that allows you to have a quick glance at whether or not your experiment worked. So you would input what types of properties you're looking for, and it would graph or analyze the data based on those properties. Future directions, to further iterate on those event impact libraries, those things that I talked about earlier that allow you to run through different contingency cases and occurrences on the power models or cyber models, that multi-axis converged modeling, historical data extrapolation, the seamless coherency, detailed sandbox environment, et cetera. So this is all the same stuff that you talk about in terms of future capabilities, but these are all the directions we're going, right? So we're not just trying to develop these capabilities, but we're moving the entire testbed in that way. So what are some of our stretch goals? On the power side, we want to do automated model ingestion. So I want to be able to take a one-line diagram from a utility that comes to me in whatever form they give it to me, a PDF even, if it's that, and automate the ingestion of that, and then be able to automatically create a model in RTDS or OpalRT or PSLF or PowerWorld or whatever tool needs to come to bear for that particular experiment, and encapsulate all of the properties of that. And that may not be, oh, I'm just ingesting a one line. I may need some other additional information like the impedance information associated with that, et cetera, to set up the power model. Or I may need multiple inputs, like I may need the one line diagram and I may need a Visio diagram of the cyber side, for instance. I want to work on reversible generation. So what I mean by that is you give me real data and I give you back what I think that system actually looked like based on the data. And I want to do that on the power side and on the physical or on the cyber side. I want to be able to include things like weather patterns. So weather drastically influences grid operation. And if you operate like there isn't weather, you're not operating like there's the real world. We want to be able to deal with synthesized outage information as well, so that it's not just that you see outages accordingly based on the power semantics of what you're seeing, say at a distribution feeder level, but that you see outages even further than that. So you get Twitter information or other things that indicate that people are out of power because they're reporting they're out of power. Incorporation of market data is another key aspect. The market greatly influences how the power grid operates, and if people manipulate the market, they can manipulate the grid in some ways. So we want to be able to do that. And the last one is both the bane of the existence of the power world, but also one of the biggest causes of outages, and that's squirrels. And so by squirrels, here I don't necessarily mean the animals, although that's what is the case for the power world. What I mean is those random things that you can't explain that happen on the grid on a daily basis that really do have an explanation, but maybe you just never actually determine what they are, but they affect how the grid operates. And so how can we create those things too? So you don't get pristine signals all the time. You may get a pristine signal that has a weird wiggle in it, and guess what that was? A squirrel. Right? And so to be able to capture those things is important as well. On the cyber side, the same types of things, but instead of squirrels, it's humans, because humans error a lot. We are the bane of our own existence in terms of security. And so we misconfigure things, we fat finger things, et cetera. And by cyber, we may fat finger things on the power side as well, set points, security settings, et cetera, that may affect the ability of a device to operate. So we need to be able to capture those human errors as well. And so here's just some of the current research projects that are underway in the testbed space. I mentioned Sandbox Environment, so we are trying to create emulation of systems by executing the actual firmware, lifting the firmware from the device, and instead of treating it like a black box, we do hardware abstraction layers, we do symbolic and concolic execution, et cetera, to be able to poke into there and provide it inputs and outputs and have it operate how it's supposed to operate, but allow us to scale it. So instead of having one physical relay, I can have one physical relay, and then I can have 1 million virtual relays that execute the exact same thing as the physical relay does. And so that's, let's say, a stretch goal. It's going to be very, very difficult to achieve that, but we're already making some headway on being able to do pieces of that today. We want to be able to also look at automated reverse engineering of things. So how can you strip away stage 1, stage 2, stage 3 delivery mechanisms of malware and get down to the point that you understand what is happening in, say, the ICS-specific payload that's there, and extract the behaviors of that, and then auto-generate code that will mimic those behaviors using our tools. So take malware, figure out what it's doing, and then create a test case that duplicates that type of ability, but is fully under your control, rather than something that was built by somebody else that may have side effects or not be as effective as what your stuff is. Instrumentation, so I mentioned that it's hard to get information from these systems. Well, we have to do this low-level augmentation as well to instrument systems where the malware may be at a firmware level on the box. So how do we do JTAG information extraction and other methods to give us internal visibility into what the hardware is doing and whether or not it's impacted by a particular operation? So let me give you an example. Systems are supposed to be designed, relays as an example, such that critical protection functions happen within a particular time duration no matter what happens to the box. So if you ping flood the box or whatever, its protection functions still are unaffected. Well, is that still true if malware is on the device in some way, shape, or form? Can those protection functions be affected in some way? And if so, how do we understand that or measure that? Well, one way is to try to make it do protection and see if it falls outside of its boundaries of when it's supposed to do things. But how do we know if the malware is actually trying to prevent that at that moment? We have to be able to peer inside the box in order to find that out. I want to be able to do deeper level analysis, so I hinted at that a bit earlier on the data analysis, but I want to be able to look at network correlation and timelining to determine the course of event propagation. So what do I mean by that? Attacker delivers stage 1 payload, which then has these conditions that trigger stage 2 payload that then take these physical actions that cause these power issues. Then these power issues then cause a cascading failure because of a stage 3 payload that gets pushed out that's doing things like set point changes or whatever. And now you have this timeline of things that happened. So if I come in at the end and all I see is this outage happened, how do I go backwards and see all of the things that happened and maintain that chain of events going both forward and backward? So if I want to recreate the event, I want to recreate the exact timings and trigger points, et cetera, that caused this so that tools can then go through and analyze it. So how do I reverse that, and how do I generate data that maintains that as I go forward and backward? Cosimulation I've already harped on a bit, but how do you look at different approaches to link together different systems that are operating at different fidelities, different time constraints, et cetera, and get them to work together? There's a lot of money being dumped into this on the national circuit. The national labs are working on a project together called Helix. NIST is working on an effort as well in this space. And there's lots of other people that are trying to tackle this as well. I'm not trying to reinvent the wheel here. I'm trying to work with those guys to all come together to find something that works for the common good of everyone, or that can be adapted into different environments. So we're evaluating different architectures and different tools that help enable that, and trying to come up with the best of breed, in essence, of these to move forward. And then, of course, configuration and provisioning is also a pain. It's not only difficult to provision some of these things, but how do you identify what it means to go back to sane or go back to good? So if I'm going to release malware on these systems and cause bad things to happen, how do I make sure that all of the bad things are erased before the next experiment starts on those systems? And so return to sane methodology is difficult inherently on that. And then the last part is it's hard to even understand what default or clean is on some of these. But then how do I automate the sanitization of that? So one naive approach is simply to burn it to the ground each time. In other words, reflash the firmware, re-image everything on the computer, be it the BIOS, the disk, the zero the RAM, zero NVRAM, et cetera. Anywhere that something may hide, zero it because you don't know where something may be. Or to programmatically determine what needs to be touched or how it was touched or how to checksum or verify that it hasn't been touched so that you can rebuild the environment in a safe way without just burning it to the ground every time, which may be impossible in some cases, may require you to do things like chip pulling or chip replacement in some cases. And so how do we automate that and make that as best as possible? So I'd like to close by thanking all of the wonderful people that have enabled us via Testbed donations, providing technology for us, providing hardware and software for us, and providing knowledge to support us in deploying these. Without them, our testbed would still just be a couple boxes on a table rather than the extensive facility it is today. And I'd like to thank all of you for listening on behalf of the whole Testbed team, all of the people that I mentioned before, and all the people that we've partnered with over the years. And my email address is there, and I'll take any questions.
First, can I get permission to ask you a question? Okay.
Go ahead.
My first question is, there's still some great voice in the academia. They claim that they don't see how to use Testbed for research. My question to you is, can you tell me why they claim? Can you support their point of view? That's my first question. My second one is about...
Well, let me answer the first one before we move on. So I think that goes right to the heart of the usability statement that I made before, which is some people don't see the value of testbeds at all, and one of the reasons is because they're inherently so hard to configure and set up for their environment. Others see the value of testbeds, but they are deterred by either not having access to the equipment or not having the knowledge on how to configure or use that equipment. And then I think there's a third camp, which is that they see the value and they have access to the things, but no one has everything they need. And so how do you create an environment that represents everything in the grid if you only have a small piece of that? And so I think the combination of what we're trying to do with combining physical assets, real systems, emulated systems, virtualized systems, et cetera, are trying to come together to help solve those and mimicking behaviors of different things to increase that usability and make testbeds more practical, improving things out. If you look at it from the alternative, what is the alternative to a testbed? Well, it's either the real systems or it's pure simulations or back of the napkin calculations to prove out that stuff works. And if you can't even understand what the full nuances are of the system, then how can you possibly reason about it on a piece of paper when it has emergent behaviors that you've never seen before? And until you actually drive real systems and see those real emergent behaviors and use the real applications, you can't possibly prove it that it works in the real world. You're just guessing.
Yeah, thank you. My second question is, during the presentation, you've been talking about the power grid that goes black out due to an attack. So my question is, can you talk a little bit about the size of the power grid, mostly in CEER research project? Because there is a configuration known by the power grid, how it works. So what I'm trying to say is, if we have a camp, for example, blackout, we have a telecommunication installation blackout, we have a region blackout, we have a sparse installation blackout, the way to approach the problem are totally different. I think you understand what I'm meaning.
Yeah.
Can you target the size of the power grid in the CEER project?
Well, I mean, so as a starting point, we start small and build bigger and bigger, right? So we start by building substation environments that allow us to look at actions at that level and their interactions with control centers. And then we move further and further up. And so distribution and transmission substations, et cetera, grid environments, regional areas, et cetera. And eventually, there may be some level of model that is, say, all the Eastern Interconnect or the whole US grid in some way, shape, or form. But they're resource-constrained problems, right? So you can only look at certain problems or certain sizes of systems at a particular level of fidelity before you just run out of resources, either computationally or otherwise, to analyze that problem. So ideally, in the end, we'll be able to look at everything, but there's a lot of work before you get to that point.
With that, Tim gets, as he always does, the last word. And I want to thank Tim for the presentation.